Good morning, good afternoon, and good evening, everyone. Welcome to the POPSIG webinar titled Process for Simultaneous Production of Functional Ingredients and Biofuels from Unused Resources in Palm Oil Refinery. I am Naomi, a committee at POPSIG. Before we begin, I would like to remind that everyone online will be muted throughout the event, by default as a norm to avoid any interference to the presentation. If at any time you are experiencing difficulties in hearing the webinar, please first ensure you have a stable internet connection. If you are unable to hear, please type in the chat box or click the raise your hand button, and our team will assist you accordingly. If you have any questions about the presented materials, please lodge your questions into the Q&A box. All responses will be given to the presenter after the presentation. First of all, I would like to introduce to you about POPSIG. POPSIG is a not-for-profit special interest group under the umbrella of the UK-based Institution of Chemical Engineers, ICHE. We focus on the chemical engineering practices in the palm oil industry. We provide a forum for the exchange of ideas, the sharing of experiences, and encouraging innovation in the palm oil processing industry. But our membership is not restricted to the chemical engineers. Our major activities are webinar, forum, university roadshow, as well as delivering newsletters, awards, and bursaries to the students. If you miss some of our live events, you can always view the summary on our newsletter webpage. Our upcoming webinars will be happening in mid-July. It will be presented by Mr. Nick Muhammad Farid Matyasi, Chief Engineer at Sime Darby Plantation, Berhad. His presentation title will be announced on our website in due course. All our webinars are free of charge and open to all. Lastly, we would like to thank to our sponsors in 2023, Desmet Malaysia, KLK Oleomas, Malaysian Palm Oil Council, POC, and Malaysian Oleochemical Manufacturers Group, MOMG, for their support to POPSIG upcoming activities in 2023. Before we move on to the presentation, I would like to introduce you to the speaker, Professor Naomi Shibasaki-Kitakawa. Professor Shibasaki-Kitakawa is a professor at Tohoku University, Japan, and also the Chief Technology Officer of Phytochemical Products Incorporated, Japan. She obtained her PhD from Tohoku University. She became a professor in 2017 and launched her university startup, Phytochemical Products Incorporated, in 2018. In 2024, Professor Naomi discovered a method for the continuous production of biofuels using the ion exchange resin catalyst, and subsequently achieved the simultaneous production of vitamin E with several practical systems in operation in Japan. Now, I would like to pass the floor to Professor Naomi for her presentation. Professor Naomi, the stage is yours.
Can I start? Can you see? Okay.
Yes, Professor, we can see that.
Okay. Thank you all for this wonderful opportunity. Today, I'm excited to share with you our technology and ongoing business activities concerning the process for simultaneous production of functional ingredient and biofuels from unused bioresources in palm oil refinery. So, first, I'd like to introduce my university. Tohoku University is located in the beautiful city of Sendai, in the northern part of Japan. As the third oldest university in Japan, it operates on the principle of research first, open door, and practice-oriented research and education. These principles attracted many students, including myself, to Tohoku University. This image shows a completed Tohoku University Science Park, and in 2024, The next generation cyclotron radiation facility, called as Nanoterrace, will be completed on this campus. Here, we hope you will make use of it for your research. Today's content is shown here. First, I will introduce the practical application of our technology, our multiple production process for functional ingredient and biofuels from fatty acid oils, rice bran. Then, I will propose the application of this technology to palm industry to achieve simultaneous production of supervitamin E and biofuel from palm fatty acid distillate. Our research target is realization of sustainable resource recycling society. A lot of research has been done, but there are few examples of realizations. Why? This is due to the lack of a technology that is both environmentally compatible and economically viable. We focused on bioresources that are generated in large quantities by existing industries and became waste because they cannot be utilized. Then we aim to convert this waste into high value added product such as fuels, commodity, foods, cosmetic, and medicine, replacing product derived from fossil resources. Traditionally, the process has been designed to maximize the economics of the target product. However, this process design method is not suitable for bioresources containing a variety of components. It's more beneficial to focus on the composition of bioresources and maximize the overall economics of the process by commercializing as many components as possible. We designed such a process as a multiple production process. We are focusing on oil production from rice bran, a byproduct of rice milling. Rice bran containing about 20% oil, which is extracted to produce functionally beneficial cooking oil. However, the process also generates non-edible oil, accounting for about 20 to 30% of the production. This oil mainly composed of non-edible fatty acid, contains a functional ingredient for health and beauty. However, they are currently banned in boilers due to the lack of economically feasible technology for their utilization. We've considered applying a multiple production process to the non-edible oil. To do this, we first examine the current status of each ingredient found in the oil. For instance, supervitamin E is currently recovered from palm oil and used in the supplement and serums. Similarly, vitamin E is produced from soybean oil. Squalene is sourced from shak, and so on. Each ingredient is derived from different raw material and commercialized through different processes. If all product could be derived from the unused oil, it's clear that this would generate significant value we have developed an innovative technology that allows for effective use of various non-edible oils rich in fatty acid. This process utilized ion exchange resin, traditionally used for water treatment, as new catalyst and adsorbent in oils. In the first column, packed with cation exchange resin, fatty acid is completely converted into fatty acid ester used as biodiesel. In the second column, packed with anion exchange resin, triglyceride is also completely converted into fatty acid ester, simply by passing through the reactors maintained at 50 degrees Celsius and atmospheric pressure. Simultaneously, byproduct water and glycerin are adsorbed onto the resin, and phenolic functional ingredients such as vitamin E are selectively absorbed as well. Consequently, the effluent from the column is a highly pure fatty acid ester, can be used as biofuel simply by removing the alcohol. In our process, no soap formation occurs, eliminated the need for conventional complex purification process. Moreover, we have developed a method to recover high purity glycerol and vitamin E during the resin regeneration. These technologies have been protected by a series of domestic and international patents. The technology is discussed more detail, including the background of this development. A similar acid and alkali catalyst combination method was proposed 20 years ago. However, due to the neutralization of homogeneous acid and alkali catalyst, additional process to remove the catalyst or their salt were required. These complex upstream and downstream processes lead to an increase in production cost, making it commercially unviable. Solid, acid, and alkali catalyst could potentially solve this problem, but no economically viable catalyst was found. We have explored the possibility of macroporous type ion exchange resins as solid catalysts. The cation exchange resin has an acid side, and anion exchange resin has an alkaline side. However, these resins are typically used for separating low molecular weight substance in aqueous systems. So there is a little understanding on how to use them as catalysts in all systems. Especially the anion exchange resin has been reported to show no activity for trans-esterification of oils. But we consider that this is because the reaction cannot proceed unless all three phases, methanol, oil, and resin, make contact. First, for trans-esterification with resin, we examine the phase state of reaction solution. In the traditional method using homogeneous catalyst, the molar ratio of oil to methanol was usually set at 1:6. Under this condition, methanol did not dissolve in the oil and created a two-phase system. However, as shown here, when the methanol molar ratio was 3.9 or less, the reaction solution became homogeneous. This rate is higher than the stoichiometric condition for transesterification 1 to 3, suggesting that the reaction would likely proceed quickly at interface between the two phases, solution and solid catalyst, just like with a conventional catalyst. Next, we set up a four-type reaction system as shown here. The homogeneous reaction solution was fed into the resin-packed column reactor. After achieving a steady state, the conversion in the reactor's effluent was determined. The result at various molar ratio are shown in this table. When using the conventional molar ratio of 1 to 6, the reaction did not proceed. However, below a molar ratio of 1 to 3.9, the reaction went to completion, achieving high conversion. This suggested that the transesterification catalyzed by the resin irreversibly proceeded even without excess methanol. Next, we examined whether the resin catalyzed esterification could proceed at low methanol molar ratio. This is a first step of the above transesterification. Normally, high conversion over 90% required excess methanol or removal of byproduct water. However, when using the resin, we achieved full conversion without needing either. As pretreatment for the resin, methanol was supplied for washing before the reaction. The methanol concentration in the resin remained high because the resin absorbed methanol much more readily than oil. As a result, the esterification caused by the resin also irreversibly proceeded, even without the excess methanol addition or water removal. In 2020, our company received investment from Tohoku University Venture Capital and completed a facility for the practical application of the resin process. Currently, various functional ingredients such as super vitamin E, bioparaffin, and phytosterol recovered in high purity and the remainder converted into biofuel. All products have been commercialized and sold domestically and internationally. Especially bioparaffin is a world's first biomass-derived material used as a base material for lipstick. We have received many inquiries from major cosmetic companies such as Seido or Chanel. The fatty acid ester are used as biofuel for power generation. We have created an innovative waste-free multiple production process. Our technology has many advantages compared with conventional technology to recover vitamin E using molecular distillation. Energy consumption is reduced by 95% due to mild condition and high efficiency. The thermal decomposition function ingredient can also be suppressed, resulting in a significantly increased yield and productivity. In addition, only biomass-derived solvents are used, with a focus on safety. Thus, we can drastically decrease the sales price of high-purity reagent. These are the equipment installed to date. The first one was in 2008 and barely worked this one. Since then, we have spent 14 years developing the equipment. A 24-hour plant will be built and operated by 2024. Our manufacturing technology and patent strategy have been highly regarded in Japan. Last year, we are honored with a visit of the Commissioner of the Patent Office. In addition, we received the Excellent Award at the Japan Manufacturing Grand Prix, organized by the Ministry of Economy, Trade and Industry. This award recognized outstanding achievement in manufacturing technologies that support industry and society. Next, I'd like to suggest applying this technology to palm industry. This is because the deodoриzer distillate derived from palm has a similar composition to that of rice bran and contains functional ingredient. First, let me explain a little more about functions of supervitamin E, a rare ingredient found only in certain oils such as rice bran and palm. It has significantly better antioxidant activity than the vitamin E. This is because supervitamin E is stable after antioxidation. Furthermore, it has excellent properties for functional food and cosmetics, not found in vitamin E. This slide shows a trend in vitamin E market. The current market size is roughly 300 billion yen and growing significantly. However, about 90% of the market comprises synthetic one. This isn't because natural vitamin E vitamin doesn't exist, but because the high recovery cost make it unprofitable, which in turn restricts production. Production of supervitamin E is even more limited, and its market is much smaller due to its higher recovery cost and susceptibility to heat degradation. As a result, a large portion of natural vitamin E is currently being wasted owing to lack of cost-effective recovery technologies. Therefore, we've estimated the potential economic value being wasted at present for deodorized distillates from four types of vegetable oils. We examine the amount of each generated and its composition and the market price to calculate the potential value of each, displayed here in red. In this calculation, we've assumed each component is recoverable without loss. Also, even per kilogram of PFAD is lower than the others. The higher amount generated shows that it can create significant total potential value. So we've extended the application of this technology to other deodorized distillate beside rice bran at laboratory scale. The results shown in this table indicate the conversion of fatty acid or triglyceride into biofuel and the recovery yield of vitamin E. This table estimates super vitamin E sales based on the experimental result and data on composition, PFAD composition, and generation from literatures. By substituting your company's specific data for PFAD composition and generation, it's possible to estimate potential super vitamin E production. And likewise, we have also conducted estimations for biofuel, specifically fatty acid ester, using our experimental result. Also, the unit of price of the biofuel is significantly lower than that of super vitamin E. The high content suggested a larger sales scale. Further separation of this fatty acid ester could increase their values as raw material for emulsifiers and functional fat and oils such as chocolate. There are various options for the use of pain, and this would depend on the specific circumstances of each factory, including factors like the scale of production and the composition of PFAD. Finally, we believe that our technology can contribute to the upcycling unused oil in your factory. Let's work together to promote bioresources circulation while improving profitability for the realization of sustainable society. Thank you for your kind attention.
Right. Thank you very much, Professor, for the very insightful webinar sharing. Now, I'm Dr. Lim, I'm moderator for today. Let's move on to the Q&A sections. What I'm going to do is I'm going to read out the questions, and then Professor, you may address each of the questions accordingly. Now, let's start with the first question. How are bioparaffin formed from transesterifications with methanol? This is referring to the content in slide 15. Professor?
No, not from trans-esterification with methanol. Rice bran oil contains a bioparaffin, but bioparaffin dissolved in the triglyceride. But triglyceride and fatty acid is completely converted to flame, so bioparaffin does not dissolve in the flame and automatically corrected.
Right. Thanks, Professor. Now, for the second questions, so the ion exchange process of converting the PFAD into supervitamin E and biofuel produces no waste or byproduct?
Yes, and no waste. But byproduct is maybe no waste. If PFAD contains a triglyceride, we maybe byproduct glycerin is produced, but maybe a little amount, maybe.
All right. Okay, thanks. Let's move on to the third question. Can I know what the equipment that installed in Japan is majorly using rice bran base oil to generate supervitamin E and biofuel? So basically, is what are the typical equipment that has been used in Japan for rice bran to generate supervitamin E and biofuel? So the current existing technologies.
How many equipment? I can't understand. So, my venture my startup company Phytochem already installs this equipment, but another company, only my company installed this equipment.
Okay.
It's
Maybe
okay?
maybe I rephrase that. Apart from this pathway, this technology path, is there any other technology or processes that generate super vitamin E and biofuel from rice bran?
Okay, maybe no, because
So,
now supervitamin E is collected by molecular distillation only. So yield is almost 20% less. So it is very difficult and it's very high cost.
okay, thanks,
You
Professor.
understand?
Yeah. All right, so let's move on to the next question. Can ethanol be used instead of methanol?
Now, in phytochemical product, bioethanol is used because the purpose of the supervitamin E production for the purpose of the safe. If we use our So our ion exchange resin method, we can use a various alcohol, methanol, ethanol, butanol. Everything is okay.
Thanks. All right. For the next question, do the PFAD requires pre-treatment before the separation technology?
No.
Okay, in that case, can I would like to follow up this question is how do you deal with different composition or the fluctuations of the compositions for, let's say, the pump-based biomass that you use?
Sorry.
Okay.
You
Since there's no pre-treatment process required, will the technology or the process, how does the technology or process deal with, let's say, fluctuations, the changes in the compositions for the feed?
we always change we design this equipment to control the resin weight, resin amount, and I extend if the fatty acid, if the contents of fatty acid content is higher, to increase the amount of cation exchange resin, or do you understand?
Yeah,
or
I think
triglyceride
yeah.
content is high,
So
controls the amount of anion exchange resin.
all right, so the menu
Only
the variable here would be you are trying to manipulate the resin amount to accommodate different okay, right, thanks.
Yeah.
All right, let's move to the next questions. What's the production output of the 24 hours plant that to be built in Japan?
Maybe main product is super vitamin E. So super vitamin E is maybe for but my maybe 40 ton, I think. 24 hours plant to 40 ton. Do you understand? 40 ton. 40 ton.
40 tons. Sorry,
Over
per day.
super vitamin E.
All right. Okay. So our next question is okay, I think the first part of the question is quite similar, which is what is the capacity of your prototype plant, which you have mentioned is 40 tons. And second part of the question is the resin fouling common in the process? And how often do you have to change the resin bed?
Phytochem product user resin maybe for 3 years. No, I think no fouling.
Okay, so basically the resin can be used up to 3 years at this point.
3 years.
And no fouling process. Yeah.
From maybe in 2020, my facility our equipment is complete. Started to produce this one, and until now we use the same resin.
Okay, all right.
At that time.
Okay.
Okay.
All right. All right. The next question is, can I know any waste generated during the cation and anion exchange process?
Waste maybe a little so there's no waste from feedstock, but we use a regeneration solution to the resin. 90% of the regeneration solution is recycled, but 10% of regeneration solution is become a waste. But that is some ethanol, water, maybe acetic acid or sodium, NaOH.
Mhm.
Do you understand? Okay.
Yeah, right. Thank you. All right.
A little.
Right. The next question is, are there similar nutrients in a palm kernel fatty acid distillate that are worthwhile to recover?
Maybe, but if I know the content of the palm kernel, I will advise our technology will be applied or not.
I think this is
I
linked to
want to
one of
know
your
the
slides. Yeah, one of your slides that you require some samples, like 50 grams of sample, if I remember correctly. Then you can do some analysis. All right.
Yeah.
Okay. All right. So next one will be, can the resin tolerate to high phosphorus content from feedstock? Will it poison the resin?
Tolerance high phosphorus contents. Acidity compound, acid compound. Only acid compound is extended to the adsorbed on the resin. So phosphorus contents. I want to know the structure, chemical structure. Phosphorus contents. High polarity is important. I want to know the contents and structure, and then I will answer.
Okay. So at this point, we were not able to tell on this. I will not able to answer this question. We have to look at the amount and also the structure. But just now you mentioned that definitely the acidic scenario or acidic situation will have this potential of this resin poison problem, is it?
Not poison. Not poison, but decrease the recovery yield of, for example, vitamin, super vitamin E.
Understand. It will affect the performance.
And increase the recovery cost a little.
Understood. Thanks. All right. Let's move on to the next question. After 3 years of usage, how is the spent resin handled? Is the resins being disposed?
Now we continue to use because there is no loss, activity loss.
I think this question is referring to for the resin, once it's reached the end of life, how do you handle or how do you treat the resin? Is it being disposed, or how it actually be disposed?
Finally, same resin, same ion exchange resin used in sugar industry. they always burned the resin. Do you understand?
It's perhaps you would like to share, is there any specific way of waste waste management of this particular resin? Is it can it be used for a very long time, and then after that, is it, let's say, going to burn it, or do we sell to a third party to dispose or reuse in another industry?
If the broken structure, if the resin structure is broken, maybe we have to dispose.
Okay. Do you aware on the disposal method? How to
disposal
dispose?
method is burned is okay. Incinerated.
Incineration. All right.
Yeah.
Okay. I see. All right. Thanks. Now,
This
okay.
is plastic.
Okay, understand. All right. For the next question, in slide 22, it shows that the composition of this super vitamin E in the palm oil is lower than the rice bran. Is there any difficulty in the recovery process?
We use adsorption phenomena, so there is no difficulty, I think. Only adsorption is especially at low concentration condition is no problem. There is no problem at the low concentration.
Understand. So it has been done in laboratory and tested, where the composition of this super vitamin E in the palm oil is able to work in the proposed technology. Okay. All right. Thanks. Now I believe one of the question mentioned that is there any regeneration of the resins required? I believe you have talked about it. Yes, you did mention that there is a regeneration of the resin. Do you like to share a little bit more on the regeneration process?
We use a regeneration process. In the regeneration process, we use a four-step, maybe four-step. First is alcohol supplied to blow out the feedstock oil inside the reactor. And then maybe acetic acid in alcohol solution was fed to replace the to ion exchange vitamin E and acetic acid to correct the vitamin E, and then suppress the maybe sodium hydroxide solution to ion exchange with acetic acid and OH ion, and then methanol, alcohol is supplied to the column. It's finished. Can you understand?
Yes. All right. Thank you very much. All right. I think there's
sorry.
No worries. There's follow up.
Very simple.
There's a follow up questions. Yeah. For this
alcohol.
Okay. Sorry. All right. For the resin, is it a type of resin that is easily available in the market, or we require a special type of resin that to get from us, a particular supplier? What type of the resin that you use or propose in this process?
Sorry. Your question
yeah. Yeah, the
is the
question
second
is
one or
correct. Yeah,
another
second
one?
one. Is the resin that you use in this process, is this a standard type or typical resin
Yes,
that
yes.
is available? Okay.
Standard type.
Okay, all right. Maybe I jump to the
It's
first
not
question if you look.
it's not expensive. Yeah.
Okay, maybe I can refer back to the first question in our list here, is that I think this is linked to the phosphorus content. So this is a follow-up question, is the example of the phosphorus content would be the phospholipid from the crude palm oil. So will it have the problem, okay, when you have this material present in your resin?
This question, sometimes I receive this question, but now we didn't know where is the phospholipid in our process. We didn't know. Maybe we don't have analysis for phospholipid, so we didn't know the behavior of the phospholipid in our process. Do you understand? Okay.
Understood. So there's a further investigation is required to tackle this specific content. All right. Okay, thank you. All right. So our next question is, what is the indicative unit resin cost for each ton of supervitamin E production? Meaning how much of the resin or the cost required?
Almost no cost. Resin cost. There is no 0.00001 yen, for example. So we stop to considering the resin cost.
Okay, this is due to the regenerations capability of the resin, right?
Yes.
Yeah, and at this point, after 3 years of operating, it still do not require any significant changes of the resin. Hence,
maybe
the operation cost.
after 1 year utilization, I check the 0.001 yen, so stop to calculate.
Okay, thank you very much. Now, okay, maybe there's one question here, is that okay, I think there's new question pop out. Let me go to that question first. The reason mentions is those commonly used in water treatment. I think this is someone that's from water treatment side. So is it the same type of resin that you use here?
Yes. Maybe in sugar to remove the sugar brown color to make a white sugar, the same resin were used in the sugar factory. Maybe I heard such a.
Okay, thanks. Now, I think this one of the question from my side is that you have shown us the performance of this process in your slide 16, which look at the yield and things like that. I believe that is derived from the rice branch, right? So do you anticipate any differences in the performance when you adapt this technology in the palm-based feedstock?
Okay, I'm sorry.
Sorry.
I want to check the slide 16.
Yeah. If you like, actually, you can go to the slide 16 to look at the performance. Yeah. So do we anticipate a very much different performance when we adapt this technology in the palm oil-based feedstock, or it will be relatively similar to what you presented today?
I think so, maybe. Different expect performance in palm oil-based feedstock. Please see the slide 23rd. I want to share.
You can reshare your slide.
Yeah. You can see? Yes,
I can see it. Now it's at slide 25.
This table shows a result of my ion exchange resin applied. The rice bran 97, 99, 87 is value, but palm is almost a similar value. So same productivity or performance will be expected in palm oil.
Excellent. Okay, thanks. I think we have few more minutes for one or two more questions. Okay, now the next question is, I think it's related to the question is, will other ion being removed throughout this process, like for example chloride?
Yes.
Okay, so it will be removed or being basically is treated as the same as a different other ion.
Yeah.
Okay, all right.
And maybe our process easily to remove fatty acid from the oil. Selectively remove the fatty acid. It is very good at removing the fatty acid from some oil. Some company request us such a process.
Okay, understood. I think there's follow-up questions here is, can you share like what are the other ions that being removed or will be removed?
Our user, I want to explain the mechanism is better, because this separation mechanism is based on the acidity of the material. So
okay.
the material has a difference of the acidity of material. Do you understand? Easily
Yes.
to stronger acidity material is easily ion exchanged by anion exchange resin.
All right, understand.
Understand?
Thank you very much.
Yeah.
Yes. Okay. All right. Thank you very much. I think just nice that we are at the end of this webinar. We are close to, in Malaysia time, 7:30 in Malaysia times. So thank you very much, Professor, for your sharing. Yeah, and thank you all for the participation and also the questions. I believe this round is one of the round that we tackle a lot of questions. Thanks to Professor that give us a very quick and short answer and accurate answer as well. Now, please, for the rest of these webinar participant, please be reminded that we will be another webinar in next month, in the mid of July. The details will be announced through our website. Now, again, thank you very much for attending this webinar, and all the best and have a good day ahead. Thank you all.
Thank you.